Evening.
It does not. Okay.
It says you're a presenter.
Yeah, hold on a second.
Sometimes it takes a while. Oh, there it is. There it is.
Uh, so can you see my?
Yes, yeah, I can. Might want to maximize your. Oh, there you go.
So do you see which screen do you see now? I mean,
I see the main slide on the left, and then the next slide in smaller on the right.
okay, hold on a second. Then I have to change it.
Yeah, full presentation mode. It's that. Oop.
Maybe I'll do with this. I mean, it shows the node, but I mean,
That's fine. That's fine. That's fine. Don't worry about it.
okay. I think for some reason the other screen is not showing up. So
Okay.
if this is okay with, then I'll continue.
Yes, please do.
Okay, so my research topic is to find a relationship of racial and ethnic diversity in urban communities with obesity. So that is the title. So, you know, public health, I mean, there are several studies have been made, and it was determined that social determinants such as national wealth or age or income inequality, different socioeconomic status, those impact health. And as along with social determinants, it is also studied that interactions among community members and the social attitude or the feelings about their society or community also impact public health. So based on these two reasons, I mean, the continuation of my previous slide is that the urban health is impacted by social cohesiveness and interactions, and ethnic composition of a community can affect these social interactions and positive social attitude. And diversity also contributes to this sense of well-being in a community. So the three factors, the social determinants, and social interactions and diversity. So these the first two factors impact health, and diversity impact both of them. So the research question is that if diversity could be a measure of public health. And there are several studies that actually prove that diversity impact social determinants. And the CDC actually listed 23 social determinants, and among them social support, social norms, residential segregation, and culture there are, along with other determinants, these are also determinants that affect public health, and all of them are also related to diversity. So based on those findings or those considerations, my study attempts to see if the racial and ethnic diversity of an urban community or neighborhood can explain the rate of obesity. I mean, the general was public health, but I chose obesity to see if diversity can impact obesity. And if there is no direct connection, is there any effects of diversity on the other predictable or predictors that can measure obesity? Now, how to rate diversity in an area? There are several research or several studies have been done in different by different people in different academia or academic settings. And the most common is to use this one. That I can never tell, Harfin-Endel concentration index, which is actually here the DI is the diversity index, and CT actually census tract. I'm going to talk about it later. So diversity index of a census tract is measured by this. The SI is the ratio of or proportion of a racial group, and the summation of all proportion and their square. If it was deducted by 1, then that would be the index, diversity index for that census tract or a smaller area. So my data sources is 500 cities project and census data. And 500 cities project was done by CDC. It actually took largest 500 cities in the United States and surveyed the different health risk factors or health outcomes. So this is a health data specifically done for 500 cities. And it is available in the city's website or on the city's website. And among several variables, it also included obesity for those 500 cities. And it was done based on census tract. And that's why the index I showed before was based on census tract. And another data source for me is census data. So I would take the census tract information and the obesity information from the 500 cities project, and then I will get other variables, the social variables or socioeconomic variables from census data for those census tract. So the reason I chose the census tract, I mean, those CDC data was available, in census tract and in for bigger areas also. I could have taken the data for 500 cities, but I choose census tract because in a bigger city, it from outside it might look a lot of diverse people live there, but in reality, those many ethnic or ethnicity or races live in different pockets. So they have separate neighborhoods or different races concentrates on different areas of the city. So it does not give, if I take city level data, it does not give the actual picture on the ground. The community still be very separated or segregated. But in a census tract, it's really small areas, and if I consider the diversity distribution in a census tract, it will give a better picture for a city, their interaction with different ethnicity or races. And for my study, I define diversity only based on race and ethnicity, not others like gender or age. The diversity could be defined in many different ways, but for this study, it is specific to race. So basically, I'm showing here the data sources. The initial data sources is this for 500 cities project. The bottom two are the main that I focused on, but for connecting different data sources, I needed to have those other variables too. And these are census data. There are a lot of census data that I started with that are the measure or the estimate of various social, economic, gender, and education factors. So these are all census data. So since it was based on census tract, and it has that CDC also had spatial data representing all those census tract, and census data also can be downloaded or they have this census tract shape files or data in GIS format. So the easiest way to connect these two data was using GIS. So I took those two different data sources and created a GIS layer that matches the census tract and all the information from census data to the census tract of the of CDC data. So I ended up with 19,765 records that represent obesity and various social variables at census tract level with samples from all over USA. So that is the uh, the spatial representation of the data. So all those points actually show census tracts. So my data is pretty much representative of the whole USA because data is coming from all over the USA. Now, the initial analysis was done in ArcGIS, which is a GIS software. So I calculated the diversity index using the formula that I showed before. In GIS, they have GIS has a tool called field calculator where I could insert the formula and populate the field. And also I use GIS for initial viewing of the data, how it looks like. So the first one here on the left shows a special distribution of obese people, and only 3 cities in North Carolina. And the other one is the income. And here is the male population, and the right side is the female population. And it's all are for those 3 cities in North Carolina. So apparently looking at that, it all look almost same. Only interesting thing is that it looks like female population is more in North Carolina and in these 3 cities than the male population. But other than that, really, you cannot, it does not show anything more or any relationship between those variables that I'm looking for. So after I created the GIS layer and did this initial analysis, and having those fields that I needed, I converted to a or I transferred that in R environment so that I could take advantage of R, do the analysis. So some columns I still, although I didn't need it for doing analysis in R, but I had it because my intention is to go back to GIS analysis and do some other spatial or do analysis with some spatial components. So that is after cleaning up all those unnecessary fields, I ended up with 19,765 records with 19 variables. And the object ID and the place tract ID is basically to be used in the GIS later. And each of the columns that came from CDC data represent the percentage of whatever variable they're representing. For example, percentage female is the percent of the female population in a census tract. So this is just a few rows from my data. Okay, this is the descriptive statistics of the data. Now you look at on the minimum is minus 66 something, which actually making the mean a negative number, and also range is really big because of that, and also highly skewed data that we are seeing. So from that statistics, we know that there is something wrong with the data. So I went back and calculated how many negative values that I had. And this data should not have any negative values. There is not a single variable where a negative value is valid. So I found the 52 values or 52 records have negative values. Or 52 negative values. If I consider that each negative value contains in a row or in a separate row, the maximum would be 52 rows. But if those negative values is shared by the same row, it will be even lower. And I have 19,765 rows. So I thought that it's better to remove all of them, and it will still not impact the sample size. Or sample size would be still a big enough one to do the analysis.
Mandy, I'm just going to jump in. I'm doing sort of a time check on you. I know these slides are really good, and I hope you share them with me. But if you could sort of given that you're 15 minutes in, maybe you should move to the key findings and the discussion of results. Okay.
Okay, okay, that's fine. So this is basically I collected the data and it looked normal, and then I calculated the correlations, and I really do not see any correlation uh, with diversity, obesity and diversity. And this is the visual exploration. So at the end, if that visual exploration does not show a good relationship between obesity and diversity. So then here I wanted to see if diversity index has any relationship with other predictor variables. And again, it's not. It shows that there are some relationship because I see this, but it's not significant. So this is the distribution of this. Some of them are really heavily skewed, and it also shows that it is possible to have near zero variance. And this is the box plot for all of this. It shows a lot of outliers, but I think outliers are valid because certain values could be concentrated in some census tracts. And is the collinearity test. There is no collinearity, I mean significant collinearity. And there is the finding. This is the conclusions from the analysis that there is no missing values in the data set, although outliers are visible, but they're probably valid values. And dataset contents feature highly varying in magnitudes, units and range. So centering and scaling of the dataset might be necessary, and transformation might be necessary as some highly skewed variable exists in the dataset. I did not find any considerable pairwise correlations, and there are possibilities of variables with near zero variance, and that might need to be removed in my analysis. And I used caret package in R, and using their function, I removed those near zero variable, and if there is any highly correlated variables that need to be removed. I used Box-Cox transformation for preprocessing the data, which also scaled and centered the data set. So 80% of the data was used for train models and 20% for the testing. So I used several models to see if there is any significant relationship between diversity. So this is, at first I used PLS as a starting point. And I saw really the importance. Diversity index is the least one, so it's not important here. Then I used random forest, and again, diversity is a little bit above, but it still is not significant. But it shows that percent of Asian is really, really important in random forest model. Then I used QBIST, again, diversity index at the bottom of the list, or near bottom of the list. Then I used neural networks, and every time as the model does not look bad. I mean, I get R square value 82%. But what I was looking, again, for this model also, there is no relationship or important relationship. Then I use GBM, again, diversity index at the bottom of it. Then I try to create model without the diversity index to see if there is any impact. And it's very little impact. You see that with DI or diversity index, the R is 76412 or 0.76412, and without it's 7647. With DI it is 6.47, and it just deteriorated a little if I don't add the diversity index. So the conclusion is that there might be some implicit relationship between obesity and diversity distribution, but it's not strong enough to make an impact. And all those models, except one that showed percentage of Asians are the most important predictor, but all other models showed higher education, especially a population that has a bigger percentage of bachelor degree holders. They have lesser obesity. So that is the finding. And the next one would be like I thought of doing some spatial analysis with with facilities like club or gymnasium, swimming pool, and what are the relationship with obesity and those facilities, and if diversity. But I'm not sure. It looks like really what I was looking for or hoping for did not happen here. So I'm not sure if that would show me anything, or that would even, or if I should be going to that to do that analysis. So basically, that's it. That's what's my finding.
All right, thank you, thank you. I just have to ask you. So, what, other than higher education, what would you suppose a stronger predictor would be then?
The bachelor degree. I mean, it's like if a population, and it's consistent in all models, the higher a population with higher degree or higher percentage of high school graduate has a positive relation. So the obesity is higher in those areas. But a population with bachelor degree or even a professional degree or graduate degree, then it's a negative relationship. So the more the degree holders are, the lesser the obesities are. And that is very strong. I mean, it's almost, in some cases, it shows a 100% relationship. So
That
so
suggests,
education has,
yeah, that suggests sort of an income relationship, an inverse relationship with income, but not necessarily along uh, degrees of racial uh, diversity, but might be because like a predominantly African American community would have low racial diversity.
yeah, but at the same time, I mean, I try to see if income has to do with anything. I
Uh-huh.
mean, apparently income should, but income that did not rank higher.
Huh.
Like education is really ranked higher than income, way more or higher.
That's interesting. That's interesting. All right, I think you have some good potential work to move on. Anyone else have any questions? Okay, well, thank you very much. That was a good presentation. Andrew,
Thanks.
want to go next?
Yes, can you hear me, Professor?
Yes, I can.
Okay.
I will make you presenter. You see that?
Uh,
Okay, I can see your slide now. Oops.
okay. I'm just switch to the presentation mode.
Okay.
So my project is based on the ARIMA and the LSTM model for stock price prediction. So ARIMA is actually a very widely used time series model for like economics data and finance data. And I think a lot of financial service company has been used ARIMA model to predict different things like interest rate and stock price for a very long time. And the advantage of using ARIMA is, first of all, it's very easy to understand, and also some simple model can generate very good result. For example, like AR1 can generate a very good result. So the model does not have to be very complicated. And the LSTM stands for long short-term memory. It's a recurrent network model, and also it's very well used for sequential data. So basically, it can be used for like image processing and time series data, and also like voice data. So a lot of large companies have been used LSTM models like Google's, Apple, and Microsoft. They all use model in their product. For example, like Amazon use it in their virtual assistant Alex product. But recently, some academics has using LSTM model for stock price prediction. So my research is based on both models. I'm trying to compare like which model is more efficient in terms of predicting stock pricing. So basically, LSTM model works like this. We have input X. Basically, it's data point in time t. Then we have a hidden stage A. Then it will yield a prediction result, Y H1. Then the next time, not only the new data point will be fed, but also the hidden state for the previous stage will be fed into the next stage model, then generate a new result. That's why it's called recurrent. So the way I did research is, first of all, I chose two stock data. One is Apple, one is S&P 500, daily closing price from Yahoo Finance. Then I fit both models. Basically, I fit a couple of ARIMA model and a couple of LSTM model for both data set. Then I picked the best model based on some matrix like AIC and BIC. And then I basically test these models against the test data set to find out the accuracy. So here is the data. Basically, I chose the data from Yahoo Finance. Basically, it's a 1 year data range. So it's from November 13, 2018 to November 13, 2019. Then I take log transformation for both data sets. Because basically we use 10, not the price. And this is how the data look like. So the left-hand side is S&P 500, the left-hand side is Apple. And the blue one is the training data set, and the yellow is the test data set. So first of all, I use ARIMA, fit ARIMA model for S&P 500, basically using ACF and PACF to find the parameters of the ARIMA. And so based on the ACF and PACF, basically I can see it's kind of like ACF, AR0 and MA0, but I chose different combinations. I chose like AR1, AR2, and the MA1, MA2, so basically a couple of different combinations. And then here's the example of the model output. So the left-hand side is the AR1 model with differentiation 1, and the right-hand side is the AR1 MA1. And basically, we can see AIC, BIC. So I choose the lowest AIC measure. So in this case, it's the right-hand side model. Then I choose this model. I use the prediction to predict the data set. So this is the prediction of the S&P 500. So based on this prediction, I can see it's actually quite accurate. The green line is the prediction, and the yellow one is the actual data, and with the band is the confidence interval. And I think it's pretty close. Then I do the same thing for Apple. So for Apple, ACF, PACF looks very similar as S&P 500. So I also tried different combinations like AR1, AR2. And here is just a different bunch of trials. So you can see the yield from different results. So like ARIMA 0 is not as good, but ARIMA 1-1 is actually a very good fit. So for S&P 500, I choose ARIMA 1-1. I think it looks better than the Apple's model. Then the next thing is after I chose the ARIMA model, I start to fit for the long short-term memory model. So for long short-term memory model, we will have different layers. Basically, we have 4 layers, like dropout layers, activation layers, and sequential layer. And this one is done using Python TensorFlow. And before we do this LSTM model fitting, we have to do a transformation for the data. Because the LSTM model has a input. Basically, I can choose how many input data I will use to predict one output data. So for example, if the input length is 5, that means I will use 5 days of price to predict the next day price. So I use different timelines to structure different model. And finally, I found like the length of 12 yield the best model. So 12 basically means I use 12 data points to predict one extra data point. Then Python will return some model result like this, like the left-hand side. And the right-hand side is the actual fit. So the blue curve is the test data. So because I only show the test data for LSTM, I didn't show the training data set, so it looks like zoom out. So the red line is actually the data. So from the graph, it looks not that accurate, but actually when I see the actual numbers, it's actually quite accurate. Then the left-hand side is basically how I construct your model. So it's a sequential model, and you can add different layers. So this model is quite simple. I use all the parameters as the default. I just change the input length to come up with different models. But in reality, I think we can try to different combination of different parameters. And for the LSTM model, we have to choose a optimizer. So I use MSE as the optimizer. So it's kind of like a linear regression. The mean square, the least linear regression model is using as the optimizer, and this one is used the MSE. We can also choose a different optimizer to come up with different models. So finally, we come up with the accuracies. So we choose 3 different accuracy. The first one is mean absolute error, and also the second one is mean absolute percentage error. Then the last one is RMSE. So I calculate all 3 metrics using test data against the predicted data. So the left-hand side is the S&P 500, and the right-hand side is the Apple data. And from this accuracy table, we can see that first of all, all of those looks very good because the error is very small. And for the Apple data, we can see ARIMA model. So the ARIMA model for Apple is kind of less accurate than the ARIMA model for S&P 500. It's kind of what I expect in my hypothesis, because I think S&P 500 has lower volatility than individual stock, so it's easy to predict, kind of really a bad result in terms of accuracy. And so I didn't expect is actually the LSTM does not generate a better result than S&P 500 than the ARIMA model, although they look kind of also a great in terms of prediction. And also another thing is the index data, the LSTM for index data does not look better than the Apple's data. They look similar, but it's not for all the model metrics, it's not higher than Apple's data. So I have some reflection. So in general, I still is a very robust model than the real model. But I think the reason why this research doesn't yield the result as I expected is, first of all, the LSTM model needs a large sample size, because like I said, you can choose different input size. So once you choose a large input size, the accuracy is gonna be improved, but at the same time, the number of prediction, the number of iteration you can do is less. So since I only choose 1 year data, I guess if I choose 3 year data for LSTM, it will yield a better result. And the second thing is, like we already see that the LSTM and also ARIMA model kind of work better than on the index data than Apple's data. So one of my hypotheses is that the reason is because S&P 500 is kind of because it's an aggregate of all stock, so it has lower volatility, it's more stable. So Apple by nature is also a very big company, a large cap company, so it's also kind of like stable. The price movement is also stable. I feel like LSTM may have a better predict power for those small cap stock because they have higher volatility, and the ARIMA model actually suggests a very steady process. So in this case, I feel like the LSTM may yield a better result. So for the future research, I think one thing we can do is, first of all, we can try a different stock to come up with different results. Then we can do like hypothesis testing to see, because in the previous table, we can see the accuracy for all the model are good, but the LSTM is less efficient than the ARIMA, but it may be not. I mean, the difference may be not statistically significant. So we have to do like use a lot of trials to come up with a hypothesis test to see if the difference is like statistically significant. If it's not, then it means at least LSTM is as good as the time series model, the ARIMA model. And another thing we can do is, like I said, we can try to use some small cap stocks to fit the model. Then we can see if the result is different. If it's different, that means maybe LSTM is a better model for like small cap or like startup company, but ARIMA model is better for the large cap company. And also we can try different like time zone, because in the IPIC, I see there's a huge spike in somewhere for S&P 500. So I think maybe it's a selection bias. So if I choose a different time range, maybe they are more stable. Kind of, for example, LSTM may generate a better result than ARIMA. And another thing for LSTM is that LSTM, like I said, it can be used for sequential data. So it's not only the stock price, but also like graphs and also voice and like news. So people who do LSTM model can integrate different data sources. For example, there is a research showing LSTM using both the stock chart, like the candle graph, and combined with the price graph, the stock price, which is more accurate than the ARIMA model. So I think this is one of the advantage of using an LSTM model. Although this research is kind of brief, and the model for LSTM is a naive model because I only change the input length, but in reality I can choose all different parameters, and I can manipulate the drop-off layers to decide how many data points I want to use for my prediction. So I think in long run, LSTM may generate a better result. There is definitely potential to do research on this method. So basically, that's my project.
Well, thank you, Andrew. Any questions for Andrew?
Yeah, I have a question.
Sure.
Yeah, so for the closing prices, did you use the adjusted or the regular closing price?
I just use the regular closing price.
And so did you account for the stock splits or stock dividends? Because they can artificially change the stock prices.
Yes, that's correct. But actually, there is no, I mean, if you see the stock history, there is no way to figure out which price is the stock split. Yeah, I think I didn't use that. But I think you have a point. If we can factor out that result, maybe LSTM model may perform better. That's why I said we can choose different time series and different time zone to do. So for example, if I choose a time zone with there is a stock split in the time zone, maybe affect my result, but if I choose another time zone without the stock split, maybe the result will be different.
Okay, thank you.
That's a good question. I mean, a good issue that you raised, Neil. That if you were to pursue this in the future, it might make more sense to try to focus on total return than just simply the change in stock price. But I guess I want to, Andrew, did that feedback on the paper make sense to you that I gave you?
Yes, I think I will make the adjustment for the paper.
Okay, right. I just want to stress upon you that, and to all of you on the call, that the final paper should be the final, final form, meaning punctuation, spelling, grammar, should be ready for prime time. But I thought it was an excellent paper, though, as I mentioned. So it's really interesting to see how neural networks overall will, how Wall Street will find a way to use them to improve upon their charting capabilities. Okay, next up we have Neil, and Neil, I'm going to make you presenter, and we'll take it away from there. And thank you, Andrew, for that presentation, though.
Thank you.
Can you see the main screen?
Yep.
Okay, great. So my project is detecting community size and whether structural changes are happening in real time. So in multi-network dynamic network setting. So let's see. So as a quick intro, the networks are a very interdisciplinary active research area. And depending on which discipline you talk to, they're going to have a different definition. So in mathematics, the common term is a graph, which is a set of nodes and edges. In statisticians like to define them as data and relationships based on some probabilistic model that they want to estimate using the data. And as a quick motivation, there's plenty of network data around us. So here is a sample Facebook social network where nodes are users and edges are whether the users are friends on the Facebook. So here we can see sort of 5 cliques or communities coded by colors. And this is a author citation network where the nodes are the authors and the edges are if one author cited another author a certain minimum number of times. But the problem in in real network setting is that the question always arises as to how do we know whether we have the right model, whether the model actually works. And to answer that question, we need to have network data where we have the right answers. So in this case, author citation network, it shows 3 clusters, right? 3 colors, but we don't know if that's the right answer. Like it could be 4 clusters. We just have to try all different combinations. So for that reason, we have a couple of really well-known real-world networks. So one is the Karate Club network. This was based on a direct observation study that this author did back in 1977. So it was a karate club at a university campus, I believe, in New Mexico. And they had an internal fight. So the instructor and the manager decided to split. And the author basically directly observed the members after the club training hours to see, which of the 2 leaders the members hung out with. And obviously there are 2 communities, right? So the blue might be the managers clique, and then the other one might be the instructors. So in this case, we are clear that it's clear that we have 2 communities. And this is a dolphin network from a paper based in from 2004. So here what we have is that the scientists placed the sensor on the backs of the whales, and they looked at the physical proximity of a pair of dolphins. And if they're close enough, then we infer interaction. And so what's funny here is that the middle dolphin, the big black circle, so when that dolphin swam away and it disappeared, then the whole community structure collapsed, meaning the whale stopped communicating. And when this whale came back, then the whale started to interact again within their community and between communities. So these are some of the things that we know are true. So as a introduction to the problem, so the key problem that I'm doing research on is community detection problem. And that is, given this graph data, how can we find the clusters that best represent the similarity among the nodes? So we want to partition, given some number k, into the community such that we have more edges within those communities than between communities. So that's a common definition. Not everybody agrees to it, but that's the working definition I'm going to work with. So the input into the algorithm is this, what's called the adjacency matrix. It's a matrix of n by n dimension, where n is the number of nodes, and the little dots are ones. So there's a one if the a pair of nodes are linked. And suppose that we're given that the right answer is 4, that there should be exactly 4 communities. Then it's easy to come up with something like this and say, hey, here's the one reasonable way to cluster nodes into 4 communities. But how do we know that it's 4? Why not 3? Right? So it could be 3. And if we try the 3, then we actually end up with a better looking clustering, right? They're more clear. There's clear boundaries. It's not as hazy as it was the case when K was 4. And also the network structure can change over time. So in this case, we have three clusters here, but the nodes now belong to different communities, right? And from here to here, from second to third one, we have an increase in K. So we went from 3 to 4. So the goal of my project is to basically figure out if we can detect when this structural change happens. Either the node memberships change or the K increases. So that leads to the project description or design. So part 1 of the project involved basically, how do we best estimate the K, right? So in this case, in the first 2 cases, we have K is equal to 3. The last 2 is K equals 4. So how do we best estimate the K? That was the task of the first project part. And the second part is to detect whether there is a change happening in a series of networks using the method that I developed in part 1. So that's sort of the quick overview. So to do this project, I needed to generate data. And the common approach in the literature is to generate data using some generative model, such as stochastic block model. And this is a very popular model. It's a random graph model. And the people use this model because we don't have enough real-world data with the right answers, where we know the exact answer. So we use SBM or variance to generate the data. So we can run analysis and see how well our models perform. So it's pretty technical here, but the key thing to note is that it's basically generating a network that you've seen before with a given K, right? So we're gonna, try K equals 3, 4, 5, and see if our algorithm can correctly detect that K. But the problem here is that the SBM assumes that if the node belongs to one community, then the probability of a connection to another node only depends on its community membership, that there is no difference among those nodes that belong to a given community. So that's obviously unrealistic. So people came up with different variants. Here's some examples. But the most realistic one, I believe, is the degree-corrected SBM. And this is where we allow nodes to have some say in whether they link up to another node or not. So here's an example of a political blog example. So the red is the conservative blocks, blue is or purple is the liberal. And we can see that if we apply the SVM, it forms this rather unrealistic clustering where the conservatives are surrounded by the liberals. But it should be more like this, where you have conservatives on one side, liberals on the other side, and that is allowed by the degree-corrected SVM. So in my project, I use this degree-corrected SVM, which is basically the stochastic block model, except that I also add this parameter psi to allow each node to have an influence on the probability of an edge. Okay, and these are some technical conditions to make sure that the math works out. So the algorithm is going to see just one simple matrix, which is called the adjacency matrix. It's a matrix of ones and zeros, one if there's an edge between the pair of nodes and zero elsewhere. And this is going to be a realization of some underlying graph stochastic process, such as the degree-corrected SVM. So this is literally what it looks like. And the algorithm is going to try to figure out what the K is, the number of communities. So obviously, human eyes can't detect that. It's really hard, but algorithms can. So some of the algorithms that are out there that are more popular are here. So I tried all of these. I implemented all of these in R. And the commonality among all these methods is that they use what's called a spectral clustering method. And what it does is we look at which of the columns in the adjacency matrices are most informative. And it turns out that there's only a much smaller number K that accounts for most of the information. So we're going to just work with those K columns. So that's basically the gist of the spectral clustering. And you can see right here. The important part here is that we want to choose the right matrix when we do a spectral clustering. So we can just use the adjacency matrix itself, or we can use one of these other, what's called Laplacian matrices. And in my project, I use what's called a deformed Laplacian, also known as Bethe, which looks like this, where A is the adjacency matrix, D is the diagonal matrix, where the diagonal elements are the degrees of the nodes. So I don't have time, so I'm not going to go through all 5, but I'm just going to walk you quickly through the top 2 and see how they work. So Bethe is basically based on this matrix called the non-backtracking operator. This became really popular when a couple of physicists proposed this idea in 90s, early 2000s. And the beauty of this is that it avoids a lot of the theoretical problems and practical problems that adjacency matrices run into when you deal with sparse data, which is what a lot of the realistic networks are. So long story short, rather than using A, I'm going to be using H, which is some transformation of the A matrix using this formula here. It's pretty simple. R is some number, A is the adjacency matrix, and D is, again, the diagonal. And here, K would be basically the number of eigenvalues that are less than 0. So that's basically what the algorithm is going to do. Okay. Pseudo likelihood is also popular. It was proposed just a couple of years ago by Sarkar and Dickel. And what they do is they recursively do a hypothesis testing, starting with K equals 1. And they're going to see whether we have enough evidence to reject this hypothesis. And they're going to keep rejecting until we come to a K value where we can't reject it anymore. Then that will be the answer for the K value. So this sounds reasonable, but what if K is really high? Then we're going to be doing a lot of hypothesis testing. So this, in my mind, is going to be less efficient of the two. But I tested all the other ones using the data that I generated in C++ because it's faster. And once I generate the data, then reading in the data in R is fast. And I ranked algorithms based on accuracy and efficiency. So here is the data generation parameters. It's pretty messy here. But the key thing to note is the rho, which determines how dense the network is, and C, which determines whether there's a big difference between and within community. So the bigger the rho and the C, the easier it is for the algorithm to detect. And I used the value such that it is not too easy. Otherwise, all the algorithms will do well. And the goal is to find the best performing algorithm. And here are the simulation results. That patient definitely outperforms. So these lines are the actual K values, which I know because I generated the data using the SVM. And these little squares are where the algorithm says the K might be. So you can see that all the other ones, like this NCV, really says it's 1 all the time, even when the correct answers are 3, 4, and 5. So we know that these are not going to work. And the throw likelihood has a big range, which is basically saying that the algorithm is not very sure about the end result. So the winning algorithm is Bayesian. So that was my part 1 of the project. And in part 2, I'm going to use the Bayesian to detect if there is a change in structure. So there are many ways to study the dynamic networks, but I'm going to use this one, multiple degree corrected SBM, by this famous paper by Chatterjee in 2015. And it's the same thing as the steady case, except now we have this superscript T to denote time. And my goal is to basically see if there's a change happening. So like in this case, that's time 1. And let's say in time I, we get a graph like this, then obviously there's a structural change. Even though K didn't change, node memberships changed. So can we do this with what we have? And so for the matrix of choice, I consider all of this, but I'm going to show you 2 of these because of time constraints. Cum sum just means adding up all of the matrices. Moving window just means adding up just the several of the last few periods and do the spectral clustering. So here are some simulation results. Cumulative sum detects it really okay, right? So in 3 periods, it gives me the correct K. So the horizontal line is the correct K, and the little dots are the algorithm's guesses. So it guesses correctly if I give it some time, and that's using cumulative sum. But the problem is that if there's a change point, then it gives me the wrong information later on. So there's some false information. If the window length is too short, then it's too fluctuating. It's not very stable. And so I have to strike the right balance. So it turns out that window length of 4 gives me the best combination. So when the change point is at 9, I find out the right next period that there's a change. And so I did some simulations where 20 iterations were conducted, and you can see that it does really well. So here is the algorithm that I came up with based on the simulation results. So the key contribution is this right here. So if the algorithm's guess on the eigenvalue is bigger than some multiple of the next biggest eigenvalue, then we're going to say that is the new K. And if that K is smaller than the previous K, then there is a phase change, that there's a structural change in the network. So that seems to work really well, because in this case, when there is a change point, you can see that it gets really close to 0. But when it gets too close, then we're going to say that that actually is a phase change. So it will trigger the return of true, which is the correct answer in this case. So for the t-value of 5, I get an accuracy of 95%. So 90% of the time, I correctly guess that there is a structural change happening. Okay, so here are my contributions. The contributions are fourfold. One is some simulation results that show that downward estimation of the K in sparse networks is informative for saying whether there is a change happening or not. And I have some comparison of the algorithms that have been recently proposed in the literature. And I have a polynomial time algorithm that people can use to detect real-time structural changes. And I have a conjecture on whether a network has a detectable threshold or not based on its parameters. So I don't have a proof for this yet, but hopefully I can put it out there as a conjecture, and members of the community can offer a proof, which usually happens in a year or two. So that's it. Here's some other information that people use in the literature, which I claim is not as accurate or not as efficient as the one that's proposed here.
This is very impressive stuff. I certainly look forward to seeing your final paper, but you, yeah, you may consider trying to get this published. This is very impressive work. Gotta say. Um, well, unfortunately we've run out of time for questions, but if you have any questions, please feel free to reach out to me. Um, Thank you all for joining the call and presenting. Again, our next call will be next week at this same time period on Monday. Any other questions, comments, concerns, or anything you'd like to share with group before we wrap up? Okay, well, I'll take that as a no. Again, very impressive work, I encourage you to send your drafts. You don't have to wait till the very deadline. You can send it to me early to get feedback. Great job, all three, and look forward to seeing you next week.
Thank you.